Hello, I hope you're doing well. Today I'm going to talk a bit about dipoles and polarization. So we're going to talk about the concept and some electric and magnetic dipoles, and then a bit about polarization, which I will probably cover even more on in another time. But anyhow, the concept is, at least for electric dipoles, it is the measurement of the distance between like a positive and negative charge. Dipole being two being two different charges, a positive and a negative. So for this one is the distance between like a positive and negative charge, which would also make sense as the units for this are coulomb per meter, or the charge per distance. Now for magnetic, very similar concept, although it can be a bit different, especially since there are no monopoles. So you'll see dipoles more often in nature for magnets, or many, like polypoles, I believe what they're called, many poles. And so what they are is that they are a north and south pole, and they are separated by like a small distance. So if you were to break apart that, you break apart its north and south pole, both magnets would then make their new north and south pole. So it will always be that, or at least as we know, there are no monopoles. And the units for this are the amp per meter squared, where an amp is a coulomb per second, which means that this overall is a coulomb meter squared per second, which we should notice is a bit different from the electric one. Anyhow, let's go into more of the concepts of these, so of the dipoles themselves. So, going back to electric, for electric, P, small case p is normally considered to be the dipole. I know it can be confused with momentum, but it is the charge per some distance, which is just the charge time distance, which would make sense as this is coulomb per meter, which this is in coulombs and this is in meters. This, of course, is also a vector, or it can be, of the charge in vector, where d is the displacement vector. D is also sometimes considered to be the dipole. So like sometimes you might see d equals this and it's the dipole. It can be weird. But anyhow, so this would mean that, for example, this would be like charge of at some vector r1 minus the charge times some point at r2, and then this is just the distance, q times displacement vector. Now, of course, there can also be multiple poles. If this is the case, that is just p times the sum of all of the charges times the distance, or displacement, or whatever the distance is, and you just kind of sum them together. And then beyond that, the charge density is, back to that dipole, the integral of distance times the density, which is the function of distance, which is differentiated by r, the distance again, 3 times y, is because this is meter right here, is the charge, right, or it's going to be in here, divided by the volume, which is meters cubed, which is the density. And then this is going to be differentiated by like meters cubed right here, because that's going to be 3 times 3 meters. So as you can see, it is just meters times charge. So just charge density. And then another important one, potential. That would be V of R, 1 over 4 pi epsilon naught times the dipole times the unit vector of R over R squared. This is actually done for the Taylor expansion. But anyhow, it can also get much more complicated. But looking at to the magnetic dipole, we can see for this that, let's just say we have some current traveling at I. We will also see some lines, this, for like the this, and then they'll like flip back around and stuff like that. Okay. For the magnetic dipole, which is a lot of times labeled as just an M, and this would be N, which is the number of turns, you'll sometimes see that, times the current right here, this current, times the area of right here. And this can also just be M times the current times A, which can also be M is equal to current dA, like so. And also something interesting of note is whether it is counterclockwise or clockwise. So if it is going, this is counterclockwise, you're going to see it go up. And then if we see it in the opposite direction, clockwise, this moves down, like so. And some other important quantities to mention, which you might see, or probably will see if you're talking about dipoles, would be like the torque, which would be for an electric dipole, would be N is equal to the dipole times electric field, or for magnetic, we'd be seeing that would be magnetic dipole time or cross product of the magnetic field. And these are, of course, vectors. And then also, something of just note, just to be helpful, potential energy, negative dot E, and it's the same thing for the magnetic. Okay, so talking briefly on polarization. So polarization is a bit interesting. It is, at least talking about the concept, it's like the property of transverse waves, which like specify like a geometric orientation of oscillations. Of oscillations. So what does that necessarily mean? Well, I will be talking a bit more about polarization at another time, but just to show you a bit, I'm going to talk to you a bit, it's a bit more advanced maybe, degree of polarization. But this is the Stokes parameter. This right here is the degree of polarization, which is based off of that Stokes parameter. But the Stokes parameter, where Q, U, and V are based off of the like orientation of the polarized wave. So Q is a linear polarization along X and Y. which if we were to see here would kind of just be like here, or it would be in this direction, the y direction. U is linear polarization along 45 degrees. So that would be sort of like here, where u is less than 0 or u is greater than 0, depending if we're going up or down. And then V is the circular polarization, where it means it's going in a circle, where if V is greater than, it's right-handed. If V is less, then it's left-handed. And if V equals 0, then there is no circular path. It is not moving in a circle. So what does this mean? A bit more. Well, this shows the wave in a couple different ways. For example, linear polarization along just one line. So if we were to see that like this, it would sort of be just along a single line. While for circular, it would be in a circle along two planes, where might be a bit hard to draw. And then the red would be in the perpendicular to that. So yeah, excuse my drawing. And then the elliptic, not the elliptical, elliptic would just be also like a circle, but just oriented a bit differently. But now, why did I talk about polarization? Well, it's because this right here is just along like an electromagnetic. However, you also will see it in matter. And what does that mean? Well, that's just because the polarization is going to be based off of the amount of dipoles per volume in their orientation. And then to just talk a bit about that, we could see the charge densities of that, where we would see the surface charge density of a bound, that's bound, P dot N, which is the N would be like the normal vector in the row, or for volume, gradient dot P. Anyhow, thank you so much. I will talk more about polarization, and we'll go further into that at another point, along with probably do some problems as well, because this is actually quite important when it comes to, for example, radiation. They talk a lot about that, like the Stokes parameter, and it is a really interesting topic, and it will start to get into combined further areas of physics, which is always very fun. But anyhow, thank you so much for watching, and I hope you all have a wonderful day.